Hello. In this video, I will continue with directional derivative and gradient. Actually, let me show you a video, an applet first. I'm going to send you a link to this, and I hope you experiment with it yourself. Before the applet, there's an excellent introduction to directional derivative and gradient. So I hope you read that. And this is the first applet on the page. There's a surface plot of a function on the left and a contour plot on the right. And you can move the point around in the XY plane. And you can also rotate that unit vector, that green unit vector. So theta is the angle from the positive x-axis, and it's in radians for some reason. And the components of the unit vector are displayed there under the angle. And then there's the directional derivative is displayed right there, if you can see the cursor. And that A is the location of the point in the XY plane. Okay. You can probably ignore A. In class, I would probably call that P in class because that's a point, a capital P. If I change the unit vector, I get a big directional derivative if it points uphill, and a big negative one if it points downhill. So it's like negative 0.7 if it points downhill, positive 0.7 if it points uphill. If it points along a contour, then the directional derivative is close to 0. So as you walk along a contour, the elevation doesn't change. So you can think of the contours as elevation contours. Suppose I move the point to the top of a hill. Then the directional derivative in any direction is very small. The same thing happens if I move it to a saddle point. Like there's a saddle point right there. There's not a minimum or a maximum, but the ground is flat there. So the directional derivative is very small in any direction. So it looks like I'll put the point at the steepest spot. It's like right there. That's where the directional derivative will be biggest. Looks like it gets up to 2.2 or thereabouts. That's about as big as it gets. Okay. Now, in the second applet, there's the same function, the same surface plot, and the same contour plot, but there's an additional element here, and that is the gradient vector. Let's see. Yeah, so the gradient vector is the red vector. The green vector is u, which you can change. And you can see that the gradient vector points in the direction of maximum increase of f. And its length is the rate of that increase. So when the ground is steep, the gradient is long, like it is there. When the ground is flat, the gradient is short, like it is at the top of the mountain or a saddle point. Okay, now below the applet on the left, it tells us what the directional derivative is and also the length of the gradient vector. And if I move u around, the biggest the directional derivative gets is the same as the length of the gradient, and that's not an accident. In fact, I gave this as part of the definition of gradient. Its length is the maximum directional derivative. Oh, and it looks like in this applet, the angle theta is the angle from counterclockwise from the gradient. So in the previous one, theta 0 was the positive x direction, but here the angle theta is the angle between u and the gradient. If that angle is 0, then the directional derivative is the length of the gradient. If it's pi, then it's -1 times the length of the gradient. If it's pi over 2, then the directional derivative is 0. So I'm going to send you this link, and I hope you experiment with this and also read the explanation. Okay, so let's get to work now. Well, I'm gonna justify something that I claimed before without proof. Last time I claimed that a couple things. I showed you how to compute the gradient. Its components are the partials of f with respect to the variables. Yeah, so that's how you compute gradient. And I also claimed that the directional derivative is, also showed you how to compute directional derivatives using gradient. And I didn't justify that. I'm going to justify that today. I'm going to define what it means for a function of more than one variable to be differentiable. And I'm going to reassure you that you're not going to be tested on this. There's not even homework on it. But I think you will benefit from it if you think about it and understand it. Okay. So suppose we have a function f of several variables. So f goes from Rn to R. Remember, Rn is n-dimensional space. R is the real numbers. And P is a point in Rn in n-dimensional space. Then we say that the function f is differentiable at P if there's a vector. It's an n-dimensional vector. I don't need to say that. B satisfying this limit. The limit as u goes to 0 of the length of f of P plus U minus F of P minus V dot U all over the length of U is 0. I guess that's just an absolute value, so make that a single bar. Well, actually, I don't need absolute values. Okay, because the numerator is it's a limit of a scalar function. Now, we're not doing a whole lot with limits as a vector goes to 0, but this just means as the vector U goes to 0 in any direction, this quantity goes to 0. Okay, so that's a definition of differentiable, and all the functions we work with are differentiable. So I'll just say that all calculus functions are differentiable. I'll say almost everywhere. So occasionally a function might have a corner or something, but if it does, it'll just have like 1 or 2 corners. Okay. Okay, so I'm going to ask you to accept this. If you accept this, then that vector, which I called V, is a gradient of f at P. Now I'm going to justify what the components of the gradient of f are. So let's take that limit and let the vector U go to 0 in the I direction. So let's take the limit as, S is fine, as S goes to 0 of f of P plus Si minus f of P minus V dot Si. If you divide that by length of Si, that equals 0. Now, if you simplify that, you get limit as S goes to 0 of P plus Si minus f of P all over S minus V dot I equals 0. Now, V dot I is just the I component of V, which is V1. And the first part is del F del X at P. So the I component of V really is del F del X. You could do the same thing with J and K. So the second component of V is del F del Y at P, and so forth. Okay, so I've justified how we compute the gradient. Now let's verify that this really gives us directional derivatives. So I'm going to do the same thing I did a second ago, but instead of using the vector well, let's do the same thing except going to 0 along the I direction. Let's approach 0 in some other direction. So let's fix a unit vector u, not because it's broken. I'll write that as u hat to emphasize that it's a unit vector. And so the limit as s goes to 0 of f of p plus su minus f of p x minus v dot su all over length of su equals 0. Now we can simplify this. There and there, the s's cancel each other out. So we can pull them out of the limit. And the rest of it is just the directional derivative. So this simplifies to limit as s goes to 0 of f of p plus su minus f of p all over s, because u is a unit vector, minus v dot u equals 0. So v dot u is the derivative of f in the u direction at p. Okay, so I just justified the way that we compute directional derivatives. Finally, I'm going to verify that the gradient has the correct length. So the length of the vector v, let's start over. So this vector v, which is actually the gradient, satisfies the following. For any unit vector u hat, v dot u hat is length v, length u hat cosine theta, which simplifies to cosine length v cosine theta. Where as usual, theta is the angle between the vectors. Now this is maximized when the angle is 0. And that happens when u hat is in the same direction as v. So u is v over length v, which is gradient of f at p over length of gradient of f at p. And when theta is 0, the dot product is the length of v. So the gradient has the direction of the maximal directional derivative and its length is that directional derivative. So now let's do some more concrete stuff and do some actual problems, examples. Not that one. Okay, so there's the problem. The function is xy over x squared plus y. Unit vector is 3/5 minus 4/5. And there's a couple questions. First one is just computing a directional derivative. And we can do that using a dot product. We need to take the gradient of f at p and take its dot product with b. Okay, well, we need to compute the gradient. It's fx, fy. Oops. Okay. I took a little break and did the partial derivatives rather than spend time on them, because we know how to do those, and that's routine. So that's the gradient of f. We need to plug in the 0.12. So the gradient of f at 1, 2, let's see, 4 minus 2 over 25. No, 4 minus 2 over 9. Del f del y is 1 over 9. So we take the dot product with our unit vector, and we get 18 over 25 minus 4 over 25, which is 14 over 25. Okay, that's the first answer. The next one is trickier, and in what direction, which is a unit vector, does f increase most rapidly at the point p? That is, what unit vector maximizes the directional derivative? And the answer is, it is the direction of the gradient. That's the direction of maximum increase. So what we have to do is take the gradient and make it a unit vector. Let's normalize it, because it's probably not a unit vector. So the gradient was 2/9, 1/9. I'm going to use a trick here that I've done a couple times. So the obvious way to do this problem would be to find the length of the vector in the denominator. I'd have to work with fractions and a square root fractions in it. Then the denominator would be a fraction. A simpler way is to multiply and divide by 9. Now in the denominator, when you multiply the length by 9, you can do that by multiplying the vector by 9. So you get 2, 1 over the length of 2, 1. That gives you 2, 1 over square root of 5. So that's the answer to the second part. That's the direction of maximum increase. That's the uphill direction. Finally, how rapidly does F increase in that direction that we just found? And there's a quick way and a slow way. I'll do it the quick way. The quick way first. Remember that the length of the gradient is the maximal directional derivative. So the easy way is the answer is the length of the gradient. So I need to take the length of 2/9, 1/9. I can use the same trick as before. I can factor out a 1/9. I get radical 5 over 9. Okay, so that's a quick way. Now, if you don't remember that property of gradient, you can just do it the usual way, the slow way. So you take the gradient of you take the gradient of f at p and take its dot product with the unit vector that we just found. So the gradient of f at p dotted with 2, 1 over radical 5. That's 2/9, 1/9 dotted with 2, 1 over radical 5. Now, when you do this dot product, you get 4/9 plus 1/9 over radical over radical 5, which is 5 over 9 radical 5. And you can simplify that, and you end up with radical 5 over 9. So that's doing it the long way. Okay. Now, it's one more thing we're going to do with gradients, one more application we're going to use. You can use gradients to find normal vectors to surfaces or orthogonal vectors to curves. So if we have a function of 3 variables, f, and we take the gradient of f at p, that's normal to the level surface of f that goes through p. Now, I don't remember how much I said about level surfaces, but a level surface is just a level set. And it's usually a surface if f is a function of 3 variables. There's a similar fact if f is a function of 2 variables. The only difference is Oops. The only difference is that the level surface is a curve. And with curves, we use the word orthogonal instead of normal. So if f is a function of two variables, then the gradient of f of p is orthogonal to the level curve of f through p. So let's use that in some examples. Okay, let's find an equation for the plane that's tangent to the surface with that equation at the point 1, 1, negative 1. Yeah, and that point really is on the surface. If you plug in the point to the left side of the equation, you really do get 2. Now, I have no idea what the surface looks like, but I'm going to draw a sketch to help me understand what's going on. Well, I can draw the point. And I'll pretend I know what the surface looks like. I'll draw some grid curves on the surface. Not an artist. Okay. Let's call that surface S. And we have a tangent plane. And for a plane, we need 2 ingredients, a point on it and a normal vector. We're given the point. We have to find the normal vector. I'll sketch what the normal vector might look like. Too skinny. I'm going to all be really creative here and call the normal vector n. Right angle thingy there. Okay. And we know how to write an equation of a plane. We get something times x minus 1 plus something times y minus 1 plus something times z plus 1 equals 0. And those 3 somethings are components of the normal vector. To find the normal vector, I have to recognize that this surface is the level surface of a function. So I'll call the left-hand side of that equation f of x, y, z. The right-hand side is a constant. So the surface is the level surface, which is called f equals 2 for short. Just like when we drew contour plots, we called the contours f equals 0, f equals 1, or whatever. This is a level level surface. We'll call that f equals 2. Okay. Now, to find the normal vector, all we have to do is take the gradient of f and plug in the point. Okay. And the gradient of f has components fx, fy, fz. That is 2y plus e to the x plus z, 2x plus 5y to the 4th z, y to the 5th plus e to the x plus z. So that's a gradient in general. We need to plug in the point 1, 1, negative 1. Fortunately, the e to the 0 is 1. So we get 2 plus 1, 2 minus 5, 1 plus 1. And that simplifies to 3, negative 3, 2. I'll plug in those numbers into the plane equation. You get 3 times x minus 1 minus 3 times y minus 1 plus 2 times z plus 1 equals 0. And that's the final answer. And I recommend against simplifying it. Ta-da! That's the final answer. Next, I'll do a similar problem in 2 dimensions involving a normal line. And we can also find a tangent line. Let's give us some more real estate here to write on. I'm going to make a rough sketch. I have no idea what this curve looks like, but I'm going to pretend I do, and it might help me solve the problem. Okay, so we're looking at the point pi 0. And that curve goes through it. I'll just draw a curve that goes through it. Don't really, I'll guess what it looks like. Ooh. Yikes. Okay. Now the first part is to find a vector that's orthogonal to C at the point. That might look something like that. Call that V. So what I need to do is express C as the level surface of a function, then take the gradient of that function. In this problem, there's a complication that there wasn't before. And that is that neither side of the equation is a constant. So what I have to do is rearrange it so that one side is a constant. And the simplest way to do that is to rewrite it as e to the x plus xy minus sine x equals 1. I'll call the left-hand side f of xy. So our curve is the level set f equals 1, not 0, f equals 1. So v is going to be the gradient of f at the point. All right, so let's find the gradient of f. It's not hard. It's fx fy is e to the x plus y minus cosine x. Comma x. Now, in retrospect, I could have solved the equation. Oh, I'm sorry. I read it wrong. That's e to the y, not e to the x. Yeah, never mind what I was about to say about in retrospect, etc. Strike that. Okay, so fx is y minus cosine x. Fy is e to the y plus x. Now, you can't solve this equation algebraically for y, and you can't solve it for x either algebraically. So this is the only good way to do this problem. So after finding the gradient, we plug in the point, pi 0. Gradient of f at pi 0 is 0 minus negative 1, e to the 0 plus pi, which is 1 plus pi. Okay, so that's the answer to the first part. Okay, next part is find a vector function to the line orthogonal to C at the point pi 0. Well, we have a point on the line, and we have a vector parallel to the line, so we just put them together, and we get pi 0 plus t times 1 plus pi. Next part is trickier, I think. Find the slope of that line. Let me sketch the line. Yikes. Yeah. Try that again. Let's have one more time. Yeah, it's better. Good enough. So this vector v is 1 plus pi. Unfortunately for all of us, that vector actually goes to the northeast. So you take the j component over the I component, and you get 1 plus pi over 1, which is 1 plus pi. So that's the answer to the third part. And after I'm done, I'm going to pause and then redraw the diagram, because it's misleading. Next part is, which really should be part 4. Find the slope of the line tangent. Well, we know the slope of the line that's normal. The tangent line has slope that's a negative reciprocal of that, which is -1/1 plus pi. And the final part is to find an equation for the tangent line. Well, I have a point on the, and this has an equation in x and y. So this is a good old-fashioned Calc 1 or algebra class equation in x and y. I have the slope, I have a point, so I use the point slope form. I won't be an mx plus b'er. Don't be an mx plus b'er. Get y minus 0, which is just y, equals the slope, which is -1/1 plus pi, times x minus pi. So that's the answer to the last part. Okay. Now I'm gonna pause and then redraw that diagram so that the vector has a correct slope. And we're back. So I redrew the diagram so that the vector goes in the correct direction. And the slope of that line is 1 plus pi over 1, or just 1 plus pi. The tangent line is orthogonal to it. So I take the negative reciprocal to get its slope, which is -1/1 plus pi. And that's it. So, and next time we will do something different.